Hello and welcome. This is a Physics Unit 4. Because it's how old I am. Physics Unit 4 video on the second part of simple harmonic motion. Now, in the first part of the video, we talked a little bit about free oscillations, what a simple harmonic motion object is, so what makes it a simple harmonic motion. And then we talked about the referencing to springs and pendulums. Now what we're going to focus on today is more of the latter part of that query. We're going to talk about springs and pendulums, but we're going to talk about them in a little bit more detail. Now what we're going to be able to do is look at the energy of springs. Now the first thing I'd like to do, I'm going to mention this is the second attempt to this video, by the way, because the first one, the pen, decided had enough, so I was scrolling through the end, so I thought I'd do another one. Okay, so what I'm going to do is I'm originally going to draw a pendulum that you generally would see in, this would be your normal sort of pendulum. So you've got your equilibrium position, I'll put E, and then you've got your two maximums. It would go up here and then sort of go backwards, so like this. Okay, so you release it from here and it's going to go backwards and forwards, as you can imagine, a normal pendulum. But we have to ask ourselves why we're watching this physics video and what we're doing with our lives. But more to the point, what I prefer to ask is what happens in terms of the energy. To understand this, what we need to think about is our gravitational potential and our kinetic. And I say gravitational potential because it's just known as potential energy. Okay, so obviously this gives a bit of an insight to what we're doing today, because I'm not just doing it for a random reason. So when we're at the top here, we've got, if you can imagine, we've got a delta H here between the highest point, which is the maximums, and the lowest point, which is the equilibrium position, which obviously is where it's going to end up after the resistance forces take effect. But for what we're considering, it's just going to keep on swinging forever and have very little, or if any at all, resistance effect. Basically, we're not worried about it stopping. Okay, so what does it start? So it starts off with high GPE and no kinetic energy. Okay, but when it gets to E, when it reaches E, it has a maximum. KE, and no gravitational potential energy, because obviously it's at its lowest point. And then obviously as it starts to go past E, the kinetic, so after E, KE decreases and GPE increases. So it never loses energy. So how would we represent this on a energy graph, for example? So what we're going to draw here is we're going to have a vertical line of energy and a horizontal line of X, or displacement to you and I. Okay, and then obviously we've got the energy here. Now we're going to call the top level energy E. Now the first curve we're going to think about is the kinetic energy. Now I mentioned at the lowest point, so E, it has a maximum a maximum kinetic energy. So for the kinetic energy curve, if the energy level is going up, obviously, as it normally does in graphs, then it's going to be at the highest point. And at the two maximums, where there is no kinetic energy, it's going to have zero kinetic energy. So obviously this is energy, so at the start of zero minus displacement, because obviously this is zero displacement, don't forget this is not zero, that's your minus, and that's your positive. So your minus displacement is going to have 0, and at your middle displacement, so zero displacement, sorry, it's going to have a maximum kinetic energy, and then at the furthest point, it's going to have 0 this kinetic energy. So the curve, hence, if you join them up properly and not make a fool of it like I've done, it's going to look something like that, and we label that curve EK. Okay, so hopefully this is starting to look good. Well, it's not hopefully, but starting to look like something slightly different, sorry. But your gravitational potential energy is going to is the opposite, because obviously at this point here at zero displacement you've got high gravitational potential, and at zero displacement it's going to be at the lowest point, so you're going to have the lowest amount of energy, and obviously that's going to continue the opposite. So it sort of looks like a double helix. So with your GPA here, your kinetic energy there. So that's what the two graphs like. Now I'm just going to pause the video while you just copy that down. Right, so hopefully you've managed to copy that down. And today we're going to go into the main event now. So hopefully that makes some sense. Obviously that's going to link into today's features, as I said, you know, it's fairly important. So I'm just going to rub all this off and then copy that diagram up again, sort of to the top right, so in the corner, because obviously this next bit's going to take a bit of mathematical skill. You'll be pleased to know I have a fair amount. So, just remember in your diagram, all I'm going to do is just redraw that curve. So you had your line, and label that A, and then it sort of look like that. Sorry, this is meant to touch the bottom, and that's meant to touch the top. That's terrible. I'm not even going to allow that actually. There's no more pen ink on this. Sorry, just I'm quite envious of that. I quite hate diagrams that aren't perfect, but it is quite awkward when you're trying to do it quickly. As long as it touches the... So I hope that look kind of okay. So that's EK, and that's EP. Okay, I mean this is ET by the way. So how can we formulate some kind of equation from this? Because that's, as I said, that's the main part of today's tutorial. So I'll just, one sec, let me just try and alter the lights a little bit to enable you to see that a little bit better. Bring the light in. Is that pen had enough briefly for a second there? So hopefully that, you can still see the labels on that. Okay, so, one sec. Right. So as you can see, this is sort of like a double helix. So they cancel each other out. So if we added these together, we're going to get this constant line, or it should be constant, ET. So basically, if we added the bottom of EP here, sorry, to the top of EK, because they're at the same point, as they can cancel out, they already reach this point. So they basically, if you were at a certain point, say B, if we're at B and we added two curves together, we'd get the line of ET. So, how can we draw, what conclusion can we draw from that? So we can say ET, the total energy, is equal to the potential energy plus kinetic energy. Obviously you could write that as EK if you want. Now we could rush in there and put EK as half mv squared, but for purposes of simplification, basically to keep it simple, I'm not going to write that, I'm just going to leave it as that, because there's a few more things we need to know along the way. Right. So what I didn't explain in that video, which I did in my previous one that I reattempted at this, I started by saying, no, you don't need to know actually, I did cast your mind back to, because obviously we're going to talk about springs for the start purpose. Because we need to build on our springs to be able to use the formula to identify the pendulum theorem. Okay, so if we're talking about a spring, cast your mind back, what do we know about springs? Now, if you did AS physics, which you should have done, you'll know that F equals K times delta L, and K being the spring constant, L being length, for F being force. And we drew a diagram that looked something like this. So your force, and then your delta L, or changing length. And when you plotted that point, it sort of looked like this, with a gradient K, because F over L being the graph is K, and you relate it to the formula obviously. And then you may have done this, your teacher may have gone into this, but under the graph you have to put some work to do a force and drag a force out over a distance. And we said that was equal to EP, the potential energy, which you can see we've got here. And we said the potential energy was equal to a half times F times delta L. Now for those more beady-eyed viewers, we did do half times K times L delta L squared. But for the purpose of what we're going to be doing, we're just going to be focusing on this equation, ignore any other equations. So you could put that other one in, but it's a little bit more complicated. Which actually we do end up using that formula part solely. But anyway, I'm going into too much detail there. So basically, you just need to remember EP is equal to half times F times delta L. And we can mix it with this equation. So F equals K times delta L. But, hold on a minute. We're not talking about AS physics anymore. We're actually talking about A2 physics. And in A2 physics, we are mentioning simple harmonic motion. We're not mentioning Hooke's law. Well, we are mentioning Hooke's law as that is a derivative of what we're trying to find here. But what I'm essentially saying is we don't going to be faffing around with delta L. So delta L can kiss it goodbye. It can go and bog off, frankly, because we don't need it. It's when you're talking about a simple harmonic motion, you're not talking about length. What we're actually talking about, kind of mentioned it in that last thing here, of displacement. Because I wrote X, and some of you in beady-eyed might think, why did I wrote X instead of L? That's because we're talking about displacement and not length. Because the length doesn't change. It's the displacement that does. Because obviously you're not going to have a pendulum that suddenly increases in length and decreases in length. It moves away from the equilibrium and towards the equilibrium. So that's why we've got L. So that's why we've got X and not L. That sounds awkward. So what we could do is we can rewrite these equations with X's in them instead of L's. So if we do that first, before I fuck around with anything else. So we said EP is equal to a half times F times delta L, but obviously we're going to use X, so half times X. And then we also said the force was equal to K times not delta L, but times X. So we can just put F equals Kx. We're going to mix these two together, put your F here into this F here. Okay? Because they're both related, as we mentioned in it for AS physics. So it's a half times F, which is Kx, times X. Simplify that down, you get a half Kx squared. Okay, so hopefully this is making sense so far. As it says, all we've done is used F equals K times delta L and put it into the equation for the potential energy under a spring, or the work done, which is actually part of this equation here. So we're not just doing this for random reasons, we're trying to work out EP, what EP is. And to do that, what we needed to do was think of what the potential energy is in the spring. And then we just simplified that into one equation, and instead of having delta L's, because we're talking about simple harmonic motion, SHM, we use X's because X is displacement, and we're not talking about length. So that's why we've changed the delta L's to X's, and we've come up with this equation here, which is EP. Okay? Alright. So, we substitute that into the equation. So, I'm not going to rewrite anything. ET equals EP, which we know is a half Kx squared plus EK. Right? Now, as I said, we do know what EK is, but for simplicity, I'm not going to write it out at the moment. Now, ET, what we said about ET, this line ET, is it's equal to EP plus EK. Now, ET is equal to EP at the maximum points when it's just EP, which is the two maximums, so that's the amplitude. So we can say ET is equal to EP at the maximum point, because as you can see, EK equals 0 at the maximum points, and it's only considered with EP. So we could use, we're going to use that. I'm not going to focus on, even though it's just at the middle, it's just EK, because there's no EP, but we're going to assume that fact that ET is just EP at the maximum points. So that's how we can formulate an equation for ET. But we can't just put EP at maximum point and write that in for ET. We've got to create some kind of formula. Now, at the maximum points, what we're essentially saying here, remember, the maximum point of displacement is what's on the bottom. The maximum point of displacement is also known as the amplitude. So, maximum displacement equals A. Now we know that the displacement is x, so maximum of x equals a. So we can just rewrite this equation we've already formulated from this with a instead of x. So hopefully that makes sense. And then put it back into here. So we can say ET is equal to half k. Now it's not x squared, it's actually a squared because we talked about the amplitude. So we rewrite that in. So it becomes a half times k times a squared equals half kx squared times ek. Now after we've done all that, what we need to do is factorise this because we've got a half of k on both sides there. So if we move the half kx squared over to the left hand side, we get ek, so it's a rewritten equation, ek is half kx because we've taken it out of both equation. So we move it over to the left hand side, so it's a half times a squared times kx. Factorise it by taking kx out, half kx is a common factor, and then we can do ek equals half of k brackets x squared take a squared. So that's your kinetic energy. Now you should know from first year, kinetic energy is half of mv squared. So rewrite that in now. We can finally do half mv squared equals half of k a squared take x squared. Now that's all very good for a pendulum. Tick tick, tickety boo, you can't do any more than that for a pendulum. So I'll just put as a little thing underneath, pendulum, sorry, that's sick. No, tickety tick, we can't do any more for a spring, not a pendulum. Let's say, giving it away there. So spring stops here, because obviously there's nothing more we can do with k or any other factor. So spring stops here. Okay, so I'll put that in a little bubble. So you know, if you're focusing on a spring, that's where you'd stop. Obviously you could simplify that to get V, but what we're going to try and focus on now is a pendulum. Now, so we go back to our old friend the pendulum. We can't have k in there. So what we have to do is go back to our knowledge of F equals ma stuff. So we are building on AS stuff, you see how it's synoptic. So we said, if you remember, F equals ma, which we said was equal to kx up here. Because that's what we're trying to get rid of. Slowly dying. So we said that was equal to kx. So we can say ma is equal to kx, and we want to get k on its own. Because we want to get rid of k. So we want to substitute something in for k. So we need to make k the subject of it. So kx equals ma. So we can say k is equal to ma over x. Now that's very good, but we need to do something else there. We can't just put ma over x. Now you should know a, so your acceleration, which is what that is equal to the angular speed squared times x. Sorry, angular speed squared times x. The displacement, sub that in, because we need to get rid of this x in the bottom. So k is equal to your angular speed, your mass times your angular speed squared times x over over x. The x's cancel, so you're left with k is equal to the mass times the angular speed squared. So that's why that is there. Alright, so hopefully this is making some kind of logical sense to you. So what we've done essentially is used our knowledge of AS physics, applied it to this, the only real bit new knowledge that we've done is this, total energy is equal to potential energy plus kinetic energy, and then we've just subbed in our values of F equals k times delta L and half of force times the delta L, and substitute delta L for displacements, because obviously it's simple harmonic motion, the length doesn't change, the displacement does. And then we've simplified it down to get this formula, and then subbed in our half of mv squared, and that's what we've got to there. But because we're now doing a pendulum, we need to get rid of the x's and the k's. So we need to get rid of the k. So we did that by subbing F equals ma into equals kx, and then rearranging ma and kx to get k on its own, and then putting in our a for the angular speed squared times x. And then that got rid of the x's, so we're using k as the mass times the angular speed squared. Now we've got k, we can sub it in here. So that means half mv squared equals half times, now we know k is equal to m times the angular speed squared, so m angular speed squared, a squared, take x squared. Okay, so just give you a minute to copy that, what we've done so far down. So then what we do, if we times both sides by a half of m, we get rid of these. So if we divide both sides by a half of m, we get rid of the half of m's on both sides. So we can sort of imagine we're cancelling these. Okay, so then we're left, because if we divide half m by half m, you get 1, which is, we can just leave that as whatever we want. 1, sorry. So that means v squared is equal to angular speed, say my angular speed donations are angular speed squared, a squared, times a squared, take x squared. Sorry, really, there's some spike in the electric current, that's why it's going funny. That's physics there. Okay, and then obviously you would square root this, so your v is equal to square root of angular speed squared, which is angular speed, times the square root of a squared, take x squared, and that's your velocity there, done. Now, we could simplify this a bit further. So you know your angular speed is your 2 pi frequency, your 2 pi frequency, or your 2 pi over t is your angular speed. So we can sub that in, so we can take this a bit further. So your 2 pi frequency times your square root of your a squared take x squared. Or if you wanted to square that all out, you could have your v squared is equal to your 2 pi frequency squared times your a squared take x squared. Okay, so what we've done there is that's your velocity for a pendulum, and then you can simplify that one to get your velocity for a spring. Okay, so hopefully, as I said, that makes some kind of sense. I hope you can see that, and that's made some, I mean, it is a little bit mind-boggling, that. But as I said, hopefully, is that a bit better? Or is that too much light? Oh great, I could have had that the whole time. But never mind, hopefully that, as I said, that helps you to understand it a little bit. Now I'm just give you a minute to copy that down before I continue with the rest of my explanation for this. So after this, I'm going to go on to damping. I'm just going to recap a little bit on what damping is. I think I did that in my first simple harmonic motion video, but I'm just going to recap it in a second. So I'm not going to be writing anything new on the board, by the way, so that can stay up there. Alright, so as I said, hopefully that makes some kind of sense. So what we did was we knew the total energy for the simple harmonic system is your potential energy plus your kinetic energy at one point, and we just used our idea of Hooke's law of F equals K times delta L, subbed in X for delta L, put the F equals K times delta L, or in this case F equals Kx, into our potential energy equation, simplified that down to get EK equals half K times A squared take X squared, and then put the equation for kinetic energy, which is half mv squared, which shouldn't change, into the equation. And then we got our final equation for a spring, but your spring stops there. And then to get in the terms of a pendulum, what we did was we tried to get rid of the x's by making F equals ma equals to kx, which we did up there. Said k was equal to ma over x, because k, if this m equals fa, f equals ma, and f is equal to kx, we could say ma is equal to kx simplified it down by kx equal ma over x, and then we subbed in a is the angular speed squared times your displacement, which obviously that's minus 1, but we cancelled it out because it's going the other way, so I didn't put minus in there to confuse you. So then that means k is equal to m times angular speed squared times x over x. X is being the displacements, x is cancelled out, so k is equal to m angular speed squared. And then we simplified that k, put that k is equal into this equation, simplified that down to get v, square rooted it, and then that's the v for your pendulum. So that makes some kind of sense there. Right, now damping. A quick note on damping. Damping, basically you have your simple harmonic motion and it's going backwards and forwards, or forwards and backwards, whichever way you look at it. Damping attempts to correct this. And now what damping does is damping introduces what we call the restorative force into the equation. So as it's going backwards and forwards, basically what you have is this motion going backwards and forwards. The damping stops this by pushing it towards the equilibrium on each way it goes. So if it's going up this way, so if it's going that way up, the angular force is pushing it this way, so it's pushing it back down. So the pendulum's trying to go over itself, the restorative force is pushing it back down. Now there are 3 stages you can have this. It's very, very strong, where it pushes it, actually gains momentum going the other way and takes a very long time to slow down, or what we call critical damping, where it just does it enough just to stop it as slow as it can. And that means you don't feel the vibrations as much as you're going through a load of rocks or on a bumpy road, which some of you might do for enjoyment and others might do for other reasons. But as you can tell, it stops it straight away. And in a rally car, when you go over bumps, it puts less pressure on the suspension and etc. It wears damps out less. So hopefully that makes sense. But if it's not going pushing it enough, because you're saying, oh, it pushes too much, it will go left and right. But if it pushes it just enough, then it stops. Well, it pushes it lightly, so it barely put any force. Then it's not pushing it over. Well, yeah, it's not pushing it over, but it's not slowing it down. So it's going to keep on doing that. So just like the heavy damping, where you try to reduce your oscillations by pushing too much, you're not pushing enough. So the momentum isn't stopped. So there's no restorative force going towards the equilibrium. But obviously, they will stop the 2 extremes eventually. But the ideally one to have is critical damping. So, as I said, I didn't go into too much detail on that one because I was just recapping what we did for our previous video. But that's the main event there on the board. So if you get that, whoopity-doo, you should be okay. Okay, so we'll see you in the next video, and thanks for watching. Any comments or anything, just let me know. So we'll see you next video. Goodbye.